in years past, it was the bottom one, the acid naming, that threw people off on that packet that I gave you over the summer, because that's the one thing that we don't cover in Chem 1. We ask you to memorize a few of the names of acids. Should I do this, Josie? We ask you to memorize HCl's hydrochloric acid, HNO3's nitric acid, but we don't go over the actual acid naming. So I want to preface this by saying there is no naming section per se on the AP exam or on any of my tests. So unlike in Chem 1 where we'd have just 6 problems of here's the name, give me the formula, or vice versa, that's not the case. Typically, what's very common is a sentence or two story problem at the top of a question, and then they give you a balanced equation for a reaction. And what you need to be able to do is look at formulas that are already there and recognize, that's the formula for barium hydroxide. A second thing that's common with them is that they are going to ask you, okay, what type of combination would this combine with that? So sodium with carbonate. Now, you were given a polyatomic ion sheet over the summer. However, on that polyatomic ion sheet, there's asterisks next to some things possibly that said memorize these, or at least some of the old versions I gave were that way. There are some common polyatomic ions that you do need to be aware of, like sulfate is SO4 with a -2 charge. Nitrate is NO3 with a -1. Now, if you don't, they will typically give you the formula for things like barium nitrate, BaNO3 2. And if you don't know nitrate's formula, hopefully you know that barium is a +2 charge, because barium, like all the other alkaline earth metals, is in the second column. So again, you'll be given a periodic table for your tests. It'll have the atomic number, it'll have the symbol, it'll have the molar mass. Some students, again, like to write the +1, the +2, again, above column 1, column 2, and then the negative charges there. Your periodic table will not give you the multiple charges, though, for the metals in the middle of the periodic table. So, for example, iron's 2 most common charges are a +2 and a +3. It won't say those little 2s and 3s like your big fold-out periodic table. So if they gave you a formula of FeNO3 3, then you have to recognize that that's iron 3 nitrate. So it's little things like that where in Chem 1 we emphasize naming a lot, because if you can't do naming, you can't do balanced equations. If you can't do balanced equations, you can't do stoichiometry. And mathematically, stoichiometry was one of the harder things we did in Chem 1. In this class, it's not emphasized the same way, because you're commonly given balanced equations on AP-style questions. They're not worried about that naming, because that's deemed Chem 1 material. That being said, I want to go over an example of all these different types of naming right now, just to remind you of how that works. So, for example, if I gave you the formula of Li2O, hopefully we would recognize that that's lithium oxide. Okay, we make the anion end in I to show that it's combined with something else, but lithium only has one possible charge, so that's that. On the other hand, if I gave you Fe2O3, again, what the College Board would expect you to know is that oxygen is a -2 anion, regardless of if it's Li2O or Fe2O3, it's a -2 anion. Iron, on the other hand, is a transition metal in the middle of the periodic table. It has more than one possible charge. So to figure out the charge of the iron, what you would typically do is figure out what oxygen is first. Oxygen's a -2 and there's 3 of them. That gives you a total of a -6 charge. 2 irons must balance that out. Therefore, this must be iron 3 oxide. Remember, the Roman numeral stands for the charge on the metal, not how many there are within any particular compound. So those were the first 2 types of naming that we went over in Chem 1. Ionic, metal, non-metal. Either the metal has one charge, like your main group element, your alkali metals and your alkaline earth metals, or it's a transition metal. Then we got into polyatomic ions, and I've already used the nitrate example. But again, hopefully we can start to recognize some of these polyatomic ions. And when you look at your polyatomic ion sheet today, if you've never noticed the pattern, a lot of things end in ate and then ite as well. An ate always has one more oxygen than an ite. So if NO3 is nitrate, NO2 is nitrite. SO4 is sulfate, SO3 is sulfite. Now Now that ate doesn't work for everything. There isn't a carbonite, but there is a carbonate. But at the same time, start looking at your polyatomic ion sheet, hopefully recognizing those patterns. Again, NO3 has a -1 charge. Now that one, just to know off the top of your head, is a little tricky. However, when we start doing Lewis dot, hopefully you'll be able to see where that came from a little bit better. So if nitrate is a -1 anion, and there's 2 of them, that must mean this is copper 2 nitrate. Copper 2 nitrate is a compound that we will be using in the lab a fair amount. We'll be creating it in the lab as well. And because some of the labs are AP required, sometimes they like to use examples specifically from those. So that's one that you specifically might see at some point. So those 3 combined wrapped up what we covered for ionic bonding altogether. Now, technically the N and the O are covalently bonded together, but what holds the nitrate to the copper is the ionic bond. Then we get into just nonmetals. Again, if you don't recall, kind of that staircase on the right-hand side of the periodic table, that separates the metals from the nonmetals. Hydrogen is also a nonmetal, though. So 2 nonmetals together is no longer ionic, it's only covalent. And in covalent naming rules, there are no charges that balance out. Again, some people would look at this, and it's a common Chem 1 mistake, where they would write charges above both things and figure out how to balance that out. But you can't balance charges on a covalent, because it's not charges, it's sharing electrons. So instead,
sorry to interrupt, is Caitlin David?
So instead, you use those Greek prefixes. There's 1 nitrogen, there's 2 oxygen. This is nitrogen dioxide. And actually, in the same lab that we make copper 2 nitrate, we'll make nitrogen dioxide, which is a brown toxic gas. We have to do that reaction in the fume line. So nitrogen dioxide, because it's all covalent. Remember, in all these types of bonding so far, we always end in a nonmetal. So if you're unsure, is it ionic or covalent, look at the first element. Metal, 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 nonmetal. And that brings us to the last one, the acid naming. And there's 3 different rules for acid naming. The simplest is hydrogen and another element. This is hydrochloric acid. Well, what if I gave you HF, hydrofluoric acid? What if I gave you H2S, hydrosulfuric acid? So it's a hydro something element-ic acid. But this one right here is one that we asked that you know. HNO3 in Chem 1 was a compound that we asked that you know. Nitric acid, no longer hydro. Get rid of that part because now it's with a polyatomic ion. And the general rule of thumb is if that polyatomic ion is an 8 polyatomic ion, it's an ic acid. I ate something. It was icky. I didn't come up with that. Someone else came up with that years ago. Unless you really like that, then I came up with it. If that polyatomic ion is an ite, nitrite, that's nitrous acid. Now again, you are not going to just see a flat-out naming section where here's the name given the formula, kind of like the worksheet that you picked up on the way, and I'm going to have you practice for a little bit here. But the more familiar you are with naming, the easier other things is. And that's the way it is with a lot of this at times, is that if you're familiar with the skills, it will help you out in the long run. So, if I go back to the Smart Notebook, the only thing I'm going to remind you of right now is what I showed my Chem 1 students of kind of a roadmap of how to do one conversion to another. Because in the middle you have moles. Moles is kind of our middleman in all of this. And then you have grams, which is one way to measure. You're going to find out that through stoichiometry and other gas law related equations, we can actually go from moles to other things besides grams. But we're going to avoid that for today. And then usually on this end we have atoms. It could be molecules. Technically, a molecule is a covalent thing, not ionic. However, sometimes we use that term. It could just be particles. It could be ions. And a mole of anything is 6.02 times 10 to the 23rd of that thing. So a quick reminder, if you were starting with this right here, and we have these other categories, if you wanted to go 2 moles, you'd have 1 mole on the top of your conversion and Avogadro's number on the bottom. Now in Chem 1, we only went to the hundredths place, 6.02. Again, on your equation sheet, it does give it to you as 6.022. If you started with moles and you were going back the other way, you'd have to have that on the top instead. And then moles to grams, you have to have grams on the top of your conversion, 1 mole on the bottom. And remember, that number of grams is the molar mass added up from the formula. Or vice versa, if I was going from grams to moles, whatever I want to solve for is on the top. Whatever I'm trying to cancel out is on the bottom. So this was quicker, quote-unquote, notes than the naming one. But I just wanted to remind you of kind of what I refer to as that roadmap. I suppose if I kind of, here's a conversion, here's a conversion. You don't have to put parentheses around conversion factors. I just thought I might separate that from the arrows a little bit better. So that skill is the second goal that we have for today, reminding you how to do that, because then what we can start to do is combine naming and mole conversions and start doing a little bit of percent composition with the last part of class. Now this last goal sheet you didn't pick up today because it's kind of divided into 2 parts. It's divided into percent composition and then empirical formula. As you can see in the bottom, it talks about empirical formula. The top one talks a little bit more about percent composition. So this is something that we covered in Chem 1. So again, today has all been, let's review stuff more or less from Chem 1 to remind you what's going on, to lead us into next class where we get into empirical formula, which if you know percent composition, we're actually doing the exact opposite next time for empirical formula. So that's hopefully the good news when it comes to figuring these things out. So what do I have written here for percent composition? If I define it's just how much of each element makes up the unit of a compound. Again, I use the term formula unit because we'll typically be looking at ionic compounds when doing this. However, it could be for a molecule as well. And then my only other point to make sure you're aware of is percent composition is based upon mass. So in other words, if we think about water as H2O, we're not going to say that 2/3 of water is composed of hydrogen. Although atom-wise, yes it is. Mass-wise, that oxygen is so much bigger that it is the majority of the percent composition of that compound. So what I wanted to do with this was the last sheet you picked up on the way, and that was called, I think, percent composition 2. I was going to do the first problem with you, and then give you a little time to work. And again, my hope would be in the 9:30-ish range, we start to wrap things up and see if we can figure out how to get onto the AP classroom. Even maybe get done a few minutes early to give you a chance to look at WebAssign as well. So if I look at that first problem on that worksheet, it gives me the written name of mercury 2 oxide, which then I would know the formula of that to be HgO. Oxygen's a -2. It tells me mercury is a +2. From there, I would look at my periodic table. Mercury is, I think, 200.59. Oxygen, 16.00. And then I'd add those 2 up. I'm getting the molar mass. But now, the only difference is, to solve for percent composition, take the part divided by the total. And that's kind of true for any type of percent composition. Typically, I'm not too concerned when it comes to significant digits for percent composition. Don't know if WebAssign will be as well. I'll check that when you guys start working here in a minute. So here, If I go to the 10th place, I get 92.7%. That means I get 7.3% for the other one. Percent composition could be done with polyatomic ions, so now you have at least 3 atoms to solve for. It looks like your question number 3 and your question number 5 on this worksheet have more than one. You could be then told, well, you have a 25-gram sample. How many grams of that sample is due to the mercury? Well, if you know the mass and you know the percent composition of it, you take the mass times that 0.927 to find your mass due to that part. So there's little tweaks that they could add on to this as well, which I believe on the bottom of this front page and on the back side, it is tweaked a little bit to give you mass values instead. I think Website might have one question that's kind of like that as well, that just gives you a value then. And now you have to multiply that by the percent to figure out how much the mass is due to that particular element. Again, hopefully that helps explain percent composition to you or remind you of that from Chem 1.